Oscillations. Why do we care? This part of the course is going to be about things that oscillate and things that wave. Some examples of oscillators to motivate this part of the course. Here we have an oscillation of the sun. It's going at about 500 microhertz, so it's a very slow oscillation. And what we're looking at actually in this frequency, in this spectrum here, this spike, represents this mode of oscillation. So this wobbling of the sun like a drop of fluid. And as I said, very low frequency. A high frequency oscillation might be silver nanoparticles or indeed other metallic nanoparticles, where here what we're doing is just shining light onto these particles from the side, and at a particular frequency the electrons will resonate and then scatter that light in all directions. So this one resonates in the green, this one in the red, these ones in blue and purple. That depends on the size and shape of the metal particle. The oscillations here are around 10 to the 15 Hertz, so that's in the optical part of the electromagnetic spectrum. Even higher, nuclear vibrations. The fluid drop model of the nucleus has energy levels that depend on the way that the fluid in the nucleus is rotating or wobbling, kind of like the sun, but a whole 10 to the 24 times faster. So all these effects are oscillations that we can understand with common physics, although they span vastly different timescales and different physical systems. Physics of oscillations is very universal, and so it's a useful thing to understand. The content plan for this part of the course, we're going to talk about single coordinate oscillations. It's like a single pendulum. Damped driven oscillations, when we add damping and driving. And coupled oscillators, where we couple two oscillators together so they can swap energy between them. We can get equations for these systems more easily using the Euler-Lagrange equation. And from the concept of many coupled oscillators, all coupled together, we can understand the origin of the wave equation and some properties of waves. Wiggles, mathematically speaking, can be described using functions like e to the I omega t for wiggles in time and e to the I kx for wiggles in space. Here omega is an angular frequency in time, k is a spatial frequency. So omega and k, they play the same role, just that this one is a frequency in time and this one is a frequency in space. That is oscillations or radians per second, this is radians per meter. By looking at some examples of oscillators, we hope to understand some universally applicable physics. That's the point of this part of the course. Some complex numbers in exponentials and trig. These are functions that we can use to simplify some of the mathematics that we'll encounter. This slide is really for your reference, so you can look at it later and know what to look up. We can convert between complex exponential notation and trigonomic notation like this, and back in the other direction like this. We can convert between radial and Cartesian coordinate systems like this, and there's a relationship between complex numbers and Cartesian coordinates because you can represent complex numbers on a Cartesian plane, and these are relationships between the trigonometric functions and the Cartesian coordinates. Some other useful trigonometric relations are these, which you have probably seen before, and sometimes if you're stuck, Mathematica can help, and there are some functions here that I've highlighted that can help with manipulating complex and exponential functions and trigonometric functions. Phasors. It can be very helpful to think about complex numbers in a geometric way, and we can do that because complex numbers are easily represented on a Cartesian plane with the real part on the x-axis and the imaginary part on the y-axis. So for example, we have two complex numbers, a and b, and we're going to add them together. We've got a being equal to some amplitude times e to the I omega t. We can imagine here, we've taken a picture of it, we've frozen it in time, we've got some phase here, omega t, which can vary in time, but it's just fixed in this diagram. And b, e to the I omega t plus delta, so there's a phase shift between a and b, delta. Well, we can add them together and we get c, right? So what's a plus b? Well, it's c. And we can write c mathematically as a plus b e to the I delta with this common factor e to the I omega t. So straight away what this tells us, if we have two oscillating functions with the same frequency and we add them together, we get a new oscillating function with the same frequency. So adding two frequencies together that are the same gives us something else with that same frequency back again. Let's go on and consider this sum C, A plus B e to the I delta e to the I omega t, as being equal to some amplitude little c times e to the I omega t plus phi, where c is some real amplitude. So this is our c here, we've got a phase omega t plus phi, and we're looking for the magnitude of this vector, which will be this number c. How do we find it? Well, we can find c and phi by setting this equation here and collecting real and imaginary parts. So here's the real part, expanding the complex exponential using this expression here. And the imaginary part looks like this. And we can solve these simultaneous equations to find c and phi. So we do that, we get an equation looks like this. So we square these two equations, add them together. We can pull out a common factor of c squared here, and we get cos squared plus sine squared, which is equal to 1. And this gives us an equation for c squared. And for phi, we can divide these two equations and find tan phi like this. Considering now the real and imaginary parts of this equation here, what we can find is equations that relate the sum of two cosine functions of the same frequency and some phase difference with different amplitudes to a single cosine function with a single amplitude and a phase. And similarly, if we're adding two sines together, then we get a single sine with an amplitude and a phase phi, with c and phi defined above. Wherever we see a sine or cosine function, we can, if we want to, replace it with a complex exponential. And to get a physical number back from that complex exponential, we just take the real part to get a cosine function, or the imaginary part to get a sine function. So, for example, we could have two functions x1, x2, that cosine functions with some phase difference between them. We could equally write that as two complex exponentials, like this, e to the I omega t, e to the I omega t plus delta. And we could add these together, or we could add these together. Adding these x's together, we have some very complicated expression like this, which comes from the mathematics on the previous slide, where we add two cosine functions together, or the real part of this. So we can just write down the real part of this number here. And so writing this down and then taking the real part doesn't take up as much space. So oftentimes it's easier just to do things in complex exponential notation. That's why we like it so much. Now, they both work, and you can just decide which one you prefer. I should also mention here that in general, the superposition of n sinusoids of the same angular frequency is a sinusoid with the same angular frequency, with some change in amplitude and phase. So this result here, we have two sinusoids added together. We could add n of them together, and we get some net amplitude and some phase, but the same oscillation frequency.